This video is going to give you an introduction to multiple linear regression. In simple linear regression, we use a single predictor variable to perform inference about a response variable. We only had one x, and we used that one x to try to predict y. However, in multiple linear regression, we can actually use more than one predictor variable to perform inference on and make predictions about a response variable. The multiple linear regression equation looks very similar to the simple linear regression equation, with a couple of extensions. Over on the left, we still have y, which represents the actual value of the response variable from the data. On the right-hand side, we have beta naught plus beta 1 times x1 plus beta 2 times x2, all the way out through beta k times xk plus epsilon. Here, x1, x2, all the way out through xk represent the actual values of the predictor variables from the data for our k predictors. Instead of just having a single predictor variable, we now have many of them. We'll let k denote the number of predictor variables we have. Beta naught still represents the true y-intercept for the line that fits the population. But now, instead of just having a single slope, we now have k slopes. Beta 1, beta 2, all the way out through beta k represent the true slopes of the regression line that fits the population. These are all regression parameters. And finally, epsilon still represents the error between the actual and the predicted values of y. The multiple linear regression line looks very similar to our simple linear regression line. On the left, we have y hat, which represents the predicted value that lies on the regression line. And on the right, we have b naught plus b1 times x1 plus b2 times x2 all the way out through bk times xk. We have k different predictor variables, again labeled x1 through xk. B naught is the statistic that corresponds to the intercept. And b1, b2, all the way out through bk are the statistics that correspond to our k different slopes. Just like we had in simple linear regression, b naught, b1, out through bk are the best estimates that we have of beta naught, beta 1, all the way out through beta k. Let's take a look at an example. We want to use age and income in thousands of dollars to predict the number of hours of television that a person watches weekly. Our first goal is to write the equation of the regression line using the coefficient output. Notice here that there's an additional line since we now have two predictor variables. Our top line still represents the intercept, but we now have a row for age and income since they're both predictors. So our regression line is going to start out with y hat being equal to 8.002, the intercept, plus 0.242 times x1, where x1 represents the age, minus 0.122 times x2, where x2 represents the person's income in thousands of dollars. Notice here that age has a positive relationship with the number of hours of television a person watches because the slope is positive, while income has a negative relationship with the number of hours that a person watches every week because the slope has a negative sign in front of it. The next thing that we want to do is make a prediction. We want to predict the number of hours of television you would expect someone who is 37 years old and makes $50,000 per year to watch every week. Our regression line is y hat equal to 8.002 plus 0.242 times x1 minus 0.122 times x2. So what we'll do to make this prediction is substitute in 37 for x1 and 50 for x2 since x2 is in thousands of dollars. Our prediction is then going to be 8.002 plus 0.242 times 37 minus 0.122 times 50. This gives us 8.002 plus 8.954 minus 6.1, which is 10.856. So what this is telling us is that a person who is 37 years old and makes $50,000 per year would be expected to watch 10.856 hours of television per week. The last two things that we need to do are interpret the intercept and interpret the slope. Interpreting the intercept in a multiple linear regression model is nearly identical to interpreting the intercept in a simple linear regression model. We're still going to set all of our predictor variables equal to 0, but the only difference is that we now have multiple predictor variables instead of just a single predictor. As a result, the interpretation of this intercept is the predicted number of hours of television watched weekly by a person who is 0 years old, where 0 gets plugged in for x1, and makes $0 per year, where 0 gets plugged in for x2, is 8.002 hours. Interpreting the slope in a multiple linear regression model is a little bit more difficult than what we did in simple linear regression. We're still going to add one unit onto the variable that we're looking at, but we need to specify that we hold all other predictor variables constant. In this case, we want to interpret the coefficient for income, which is x2. What this means is that we're going to add on $1,000 to a person's income, but we're going to hold their age, which is x1, constant, so that it doesn't affect our prediction at all. We don't want to be varying x1 while we're also simultaneously adding something on to x2. So our interpretation for the slope coefficient is, for every additional $1,000 that a person makes per year, holding their age constant, the predicted number of hours of television watched per week is expected to decrease by 0.122.